Hello, PCHers. Welcome to Chapter 13. This is going to be an introduction to matrices, which are quite useful as a shorthand for working with multiple equations or vectors. And so what we're going to do in this lesson is we're going to define the matrices and their components, learn how to add and subtract matrices, multiply by a scalar, and multiply two matrices against each other. All right, so let's start off. What is a matrix? So you can see, first off, notice that it has like this little bracket. So that is representing that these are matrices. So we have dimensions for a matrix, and it's really important to understand how this works, because if you don't have the right dimensions, you can't necessarily add or subtract. So matrices are made up of rows. So these are your rows, and then your columns. And so we always, when we're talking about the dimensions, it's always the row by the column. So this would be a 2 by 3. This would be next one is a 3 by 2. This one here is a 1 by 4, etc. All right. An n by n matrix, in other words, the same number of rows as the same number of columns, is referred to as a square matrix, and it actually gets some special properties that we will work with later on. And then you have every number in that matrix is called an element. So for instance, this 5 right here is in row 1, column 1. And so that's how we would represent that element. -4 right here is in row 2, column 2, etc. All right. Two matrices are going to be equal if and only if they have the same, exactly the same elements in the same position, of course. And the main diagonal starts here and then goes down. And in a square matrix, this is very important, because in a square matrix, you can do some what's called row reduction to solve systems of equations with it. And then we have, that's going to then be called the diagonal matrix, is a square matrix where you have zeros off of the diagonal. So you can see we have the main diagonal and zeros off. In the interest of time, there's some things we aren't going to cover with these square matrices, but we're going to get to as much as we can. All right? Okay, so let's get into adding and subtracting. Super easy. All that you have to make sure of, though, is that you have the same dimensions. That is important, because basically you're going to take the same element. So this is, first of all, this is a 2 by 3, and we're adding to a 2 by 3, and our result will be a 2 by 3. So I'm just going to add corresponding elements. So 5 plus 4 is 9, 2 plus 6 is 8, 7 plus 8 is 15, 1 plus 5 is 6, 3 plus 1 is 4, 9 plus 3 is 12. And that would be the result. And if you're doing subtraction, it's exactly the same. So notice we have a 2 by 2, and we're subtracting from a 2 by 2. So we get 6 minus 4 is 2, 5 minus 7 is -2, 2 minus 5, -3, 3 minus 2 is 1. And that's really all there is to adding and subtracting. It's super easy. Multiplying by a scalar is also super easy. All you're going to do, it's just basically distribution. All right, so this 5 is going to distribute to everybody. So this will become 10, and this will become 15, 20, 30. 5 times 1 is 5. 5 times 7, 35. That is it. But hang on, because there's more. So if we have two matrices that are equal, so we know that they are equal, then we know that the corresponding elements So you can kind of utilize that to solve. So I happen to know, here's 5x plus 2, here's 12. They're both row 1, column 1. So I know that 5x plus 2 has to equal 12, which means 5x equals 10 and x equals 2. And then let's see, what other variables do we have here? We have y minus 4 is going to equal a negative 8. So y is going to equal, if I add 4, a negative 4. Give that one a box. And then our last element is z. So we have here 4z, 4z plus 6 equals 2. 4z equals negative 4. So z is a negative 1. So that's not too hard. You're just matching up corresponding parts or corresponding elements in your matrices. Now we get into multiplying. So multiplying is sort of like rubbing your head and patting your stomach at the same time. So what's going to be important here is making sure the inner dimension is the same, and you'll understand why when we start. The product, the end result, will be the outer dimension. So let me give you sort of an example up above. If I were to give you a 3 by 4, I guess I give it to you right here, and oops, but I wrote it. Okay, so let's say we started with I have to rewrite this. Sorry about that. Okay. If I gave you a 2 by 3, and I wanted to multiply that against a 3 by 4, these are your inner dimensions. So they match up. So in other words, the columns match up with the rows of the second one. My result is going to be the outer dimensions, which would be 2 by 4. So these would be your outer dimensions. All right. So the way it works is you are going to take a row and you multiply it against a column. And so when I do that, and then you add each successive product. So I have A1 gets multiplied by X1. So that's kind of here. I'm going to actually write it out in terms of, so you have row 1, column 1 is getting multiplied, well, you have row 1 is getting multiplied by column 1. And so that is what is represented here, where I would have the A1 times X1, and then you add after you do your multiplication. So this would be row 2, column 1. This would be row 1, column 2, and I can even color code this actually. So row 2 with column 1 would be that. So we would have row 2, column 1, and then I could have row 1 with column 2. So row 1, column 2, and then the last one would be row 2 with column 2. All right, I don't know if that made sense. Let's just actually do it. I think it makes sense sometimes just to get in there and let's get our feet dirty. So we have here a 2 by 2, and here we have a 2 by 3. So my inner dimensions match, and I know I expect my result to be a 2 by 3 in terms of dimensions. What makes that nice is that you can then sort of plan ahead for the size of your matrix. So I'm going to really do every single step here. So we're going to do row 1. That was not row 1. Dun, 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 dun. Row 1 with column 1. So I'm going to have 7 times 3 plus 0 times 5. And we'll simplify this when we're done. All right, so that would be row 1, column 1, the result. Now what I'm going to do is row 1 with column 2. So that's going to be 7 times a negative 3 plus 0 times 4. Okay. Now I'm going to do row 1. Oh, maybe I didn't give myself enough room here. We'll do that at the end. So now I'm going to do row 1 still with column 3. So that's 7 times 6 plus 0 times a negative 2. So you can see what I mean by like rubbing your head and patting your stomach, because you're going horizontally with one of them and vertically with the other, is basically, I guess, how I could describe it. Now we get down to, we are done with row 1, and we're going to work on row 2. So first we're going to go back, and we're going to go row 1 with column 1. Sorry, row 2 with column 1. So that's going to be 5 times 3 plus 3 times 5. So now we're done with that. We're going to do row 2 with column 2. So 5 times a negative 3 plus 3 times 4. And then we still have row 2 with column 3. So 5 times 6 plus 3 times a negative 2. And usually I wouldn't actually write this all out. As you get better with it, you just go straight to your answer as you're working it out. So we can see we're going to get 21 in that first position, and then I'm going to have a negative 21 in this row 1, column 2. Then I'm going to have 42 here. 15 plus 15 is 30. And negative 15 plus 12 is a negative 3. 30 minus 6 is 24. And notice we do have a 2 by 3. So that would be multiplying. Now, sometimes, because you have to have this matching of the inner dimension, multiplication is not necessarily going to be commutative, meaning A times B is not going to equal B times A. It will work always when you have a square matrix, but so this was D times E. Again, order matters. So D was the first matrix where we used the rows, E was the matrix we used the columns. If I switch it, then what I'm trying to do is multiply a 2 by 3, because that was E, against a 2 by 2, and notice my inner dimensions do not match up. So that means that when I tried to do a row against a column, you wouldn't have the same number of elements. So the inner dimensions don't match up. So it's not possible to do the multiplication. All right, now this one's going to be really fun. So we have a 2 by 2 against a 2 by 2. So actually it doesn't even matter which order we go in, but we're just going to do A times B, and this is going to give us a very special matrix. So let's see how this works. It's hard to show this in a video, so I'll show you in class, but when I'm doing them, I'm using my 2 kind of pointer fingers and going, vertically for the rows or horizontally for the rows and vertically for the columns, so I can kind of just work it out. But I'm going to show the work here. So we have 3 times, I'm going to do row 1, column 1. So this is going to give me 3/5 plus, because a negative times a negative, 2/5. All right, we did that one. So now let's do it against, I like to stay with my rows and do all the columns. It really doesn't matter. You'll find your own pattern. So this will be 3/10, and this will be minus 3/10. And then I'm now going to move to row 2 and column 1. So that's going to be 4/5 minus 4/5. And then we get to, so we're done with that. So row 2, column 2 is going to be 4/10 plus 6/10. And the result, drum roll please, is going to be 1, 0, 0, 1. This is an important matrix. This is called the identity matrix. And the identity matrix is always a square matrix. It always has 1 on the diagonals and zeros off the diagonal. And what's special about it is just like multiplying by 1. In other words, I'm going to put 3, 4, negative 1, 2, our old A matrix here. And notice what I get. Hey, stop that. Where'd my pen go? So I get 3 plus 0, and then I get negative 1 plus 0. Then I get 0 plus 4, so I'm doing my finger thing right now. And then I get I get 0 plus 2, and voila. So notice your identity matrix, we usually use a capital I, times A equaled A. So it's like multiplying by 1 in matrix form. All right, so that is your basic introduction to matrices.